Hey everyone, so this is going to be the last thing to talk about before we get into one of the major aspects of this unit, where we're actually going to talk about how to find the period of this harmonic oscillator. You know, we've been constantly talking about these objects, pendulums, springs, circular motion things, these systems where they repeat their motion periodically over and over again. We found some ways to find period, but are there any other ways? It turns out that yes, we actually can find the period for an oscillating spring based off of the system's characteristics themselves. The equation that we have for the period for a spring system is 2 pi rad m divided by k, where m is the mass of the system, in particular the mass attached to the spring, and k is the spring constant itself. There is a derivation to this. I'm not going to show it because it's not really necessary. And if anything, it's going to be a little bit more confusing than helpful. With a lot of the other things that I've derived, I found it important because it could lead you into other derivations that you might do, like finding the work, showing you how to find the potential energy through doing area under the curve is useful because if I give you a different type of force, you can find the potential energy through that method. With this, there's really not much else you could do with this. You're not really going to be expected to have to derive this. Like I said, it can get a little complicated, so it's fine. Just believe me when I say this is the equation. And that's pretty much it. We're going to do some practice with this, and now I'm going to show you another one. So here's the first question. Pause the video, work itself, and we'll go in a second. All right, so for this, we want to know what the period of the oscillation is. So, well, we have the mass, we have the spring constant, we plug them in, and we get 0.314 seconds. All right, now the next question. Now, in order for me to explain this, in order for me to go over this, I need to explain the setup because it is a little bit unclear in the wording. So the spring is unstretched. It's just hanging naturally. The block is attached to it. It's not hanging from it yet, but it's just attached to it but held at rest. Then the person releases it and it's going to end up oscillating back and forth. We want to know what would the amplitude be for that oscillation as we drop it from that point. Now, there's two different methods to solve this, and there's a good chance that you might have used one, but you didn't complete the problem. So I want to make sure that I show both methods and explain the reasons for both. So the first method is we're going to use forces. Now, when we drop the object at that point, much like a pendulum, where we drop it at a height and it will constantly return to that height, that initial drop point becomes the amplitude point of the motion. So when I drop this block, when it's attached to the spring and it starts oscillating, it's going to constantly return back to that initial drop point that I had before. Because I didn't throw it down or do anything like that, there's no reason for it to go above that point. There's no energy being lost through friction or anything, so it's not going to reach amplitudes lower than that. So it'll constantly reach that same initial height. So that point is going to be my amplitude. Now the amplitude is measured from the maximum point, the maximum displacement, to the equilibrium point. So I can use forces to ask myself, well, from that initial unstretched section, how far would it go to reach the equilibrium point? Equilibrium point for the spring being when the gravitational force and the spring force are equal to each other. So that's going to be my first setup, setting the spring force equal to the gravitational force. I plug my numbers in, and I end up getting that the amplitude is 0.025 meters. Now, the second method I use is probably what a lot of other people try to do, and that's energy. However, we have to be really careful with this. Unlike the horizontal cases and the pendulum case, when we have a vertical spring, there are technically three different types of energies. There's gravitational potential, spring potential, and kinetic energy. So a lot of people will probably try to do spring potential goes to kinetic energy, or because that's what we've done in previous parts. Or maybe you try to do gravitational equals kinetic. But if you do that, you're not doing the whole picture, because a lot of times when you have the kinetic energy, it's at a point where the spring is stretched and all these other things. So besides the fact that we don't have any information about the speed, that won't really help me. So the only one that makes sense is for me to find a point that is purely one type of energy and set that equal to another point that's purely that one type of energy. The 2 points are actually going to be the very beginning. So when I'm holding the block onto this unstretched spring, there's no stored potential energy in the spring. There's no kinetic energy. All the energy is stored in gravitational potential energy. So I can start with gravitational potential. Then when I release it, that gravitational is turning into potential and kinetic, potential of the spring and the kinetic motion. And so as it falls, it's going to have a combination of both up until it gets to the other amplitude. When it gets to the second amplitude, the negative amplitude, all of the gravitational potential energy is away because that's the lowest point. Or maybe I should say the gravitational potential becomes its minimum value. The kinetic energy becomes zero because kinetic energy is always zero at the amplitudes. So the only energy remaining is spring potential. So I can do the gravitational potential equals the spring potential. I set the equations equal to each other, and if you draw the picture, it'll make a lot of sense. But the height in the height drop, the difference in the height between the 2 points is going to be x. And that's going to be the same x as how long the spring has fully elongated. So in this case, x is not being used as the distance between a point to the equilibrium point, but just from unstretched to fully stretched. So when I do this and I start plugging my numbers in, you'll notice something about the number. I end up getting x equals 0.05. And you'll notice that's not what I got before. Well, how is that possible? This should get me the same answer because logically it's sound. It makes sense. Well, the reason why is because we have to divide that answer by 2. Because when I start at the very top, I'm starting at the positive amplitude. It goes down, it passes the equilibrium point, and then goes to the negative amplitude. So it'll do something like this. So it starts at positive amplitude. There's the 0 point, and then there's the negative amplitude. The x that I found is this entire distance, which is a plus a, or 2a. But I'm not concerned. I don't care about what that full distance is, how long it fully stretched. I care about what the amplitude is. I care about this distance from the amplitude to the equilibrium point. So when I do this, I have to divide it by 2. I have to take it one step further. So some of you might not have realized that. That's fine. Like I said, this can be a little tricky, especially if it's your first time. But once we start talking about the graphs that are related to simple harmonic motion, this stuff should start making a little bit more sense. All right. Here's the next question. Pause the video, work yourself, and you'll go over in a second. All right, so this was actually just a one-on-one question, basically showing the relationship between mass and period. We look at the equation. We can do the 1-1 method. The key thing here, though, is to remember that the constants, the 2 pi, they become 1. Remember, when we do the 1-1 method, we don't care about the constants. We don't care about any halves or twos or pi's in this case. What we care about are the variables. So if you wanted to, you actually could have just rewritten as t is proportional to, if you wanted to, be really careful, m over k. Since m's the only one that's actually changing, I could actually then rewrite this again as just being rad m, get rid of the k. And I could do the 1-1 method with this, where I'm just plugging in 2 for m, and I'd end up with the same result. I didn't clarify in here, but I wanted this to be answered in terms of t. So I'm going to make sure to actually rewrite that, but this is going to be in terms of t. So the answer should be t rad 2. All right. So that was dealing with the the period for simple harmonic motion in a spring. Now let's have a little quick talk about pendulums. So as I've been constantly saying throughout a lot of these videos, that the stuff that we talk about with springs can be directly applied to other simple harmonic motion, in particular pendulums. Springs and pendulums actually have a very one-to-one type of setup where pretty much everything that happens with the spring happens almost exactly with the pendulum. There are a few differences, of course. For example, instead of spring potential turning into kinetic, now we end up having gravitational potential turning into kinetic, as obviously we've gotten rid of the spring and are now using gravity. Another thing that I had mentioned before is that the restoring force that's producing the periodic motion and the simple harmonic motion, for the spring, it was the spring force that acted as this restoring force. But now with the pendulum, it's going to be some weird combination of tension and gravity. Um, it's a little bit complicated. You honestly wouldn't be asked about the restoring force for a pendulum. You'd mostly be talking about the restoring force for the spring. Now, there is actually one other major difference. If you looked at the equation for the period for a spring, gravity was not a factor in there. The only factor was mass and spring constant, meaning that it didn't matter how far down I pulled that spring. I could have pulled it down 1 meter, half a meter, a million meters. The period will still be the same. Now, this seems like it wouldn't make sense because the object is now traveling a much further distance. Why wouldn't the period be shorter or at least different? And that's because while, yes, the distance is greater, so is the speed. The object now has more potential energy that can be turned into kinetic energy, or maybe less potential depending on if it's being pulled shorter. So the speed will actually change accordingly such that the period always remains the same. In addition, the spring works in space. It works in a spot where gravity either doesn't exist or is extremely heavy or extremely light, doesn't matter. The spring would work the same way and would still have the exact same period. The only difference between doing a spring on Earth versus oscillating the same spring on Jupiter is where it does its oscillations. So it will just basically, because of gravity being much stronger on Jupiter, the spring's equilibrium point would be much lower. So it would be oscillating lower down, closer to the ground, but it would still oscillate with the same period of its motion. All right. So with the spring, those were two things that were fairly important. That the where it was released didn't matter, and gravity didn't matter. However, that same statement is not going to be the same for the pendulum. It turns out that the pendulum is gravity dependent. Again, this makes sense. Gravitational potential energy is in the energy setup. If I try to imagine a world where there is no gravity, then there's no force to pull it down to even start the motion. So why would the object experience a pendulum motion? So a lot of this stuff ends up making a lot of sense when we start thinking about actually adjusting gravity and seeing how that might affect the pendulum. Uh, so the equation that we have for the period of pendulum is actually very similar for the spring. It's 2 pi rad L over G. L is the length of the pendulum, usually the length of the string, and G is the gravitational acceleration. So the planet you're on, things like that. Now, one thing that's actually important to note, we're actually going to do experiments on this where we actually test whether or not this relationship is true, what factors do or don't. One thing that's important though is that This is sort of an approximation. Realistically, this actually should have a little approximated equal sign because this isn't the full story. It actually turns out that unlike with the spring, where we drop the pendulum actually does have an effect on the period. However, it's such a small effect that it's considered negligible as long as we keep our angle fairly small. So the actual equation for the period of a pendulum looks like this. Now, here we could see the theta. This theta is the angle in radians that is being released from. Now, what scientists do is when they see something like this, where they have a term being squared and quadrupled and sextupled and octupled and all that, they look to see what are the ranges that that number can go. For this, uh, since it goes up to pi, and not pi, 90 degrees is essentially typically the highest that a pendulum would go. Theta usually ranges somewhere between 0 and 1.6 ish. For the most part, that's a fairly small number. And if I take a small number, especially if it's less than 1, like 0.5, if I square 0.5, I end up getting a smaller number. I get 0.25. Where is it? 0.25. And then when I raise it, that should be going over here. If I take 0.5 and raise it to the power of 4, then it gets even smaller. It becomes 0.0625. And raising it to the power of 6 brings it even smaller and smaller and smaller. And the smaller this theta is, the smaller their squares and fourth powers and sixth powers become. So what scientists use is what's called the small angle approximation, which basically says that if the theta value is really, really, really small, then this approximation, this theta squared, theta to the fourth, theta 6, is essentially gone. We can ignore that part. Also, we can ignore the fact that there's technically a sine theta in there and just replace it with a theta. There's a lot of things that scientists do to kind of simplify it. So you don't need to really worry about that too much. I'm only putting this in there for the experimental side because one thing that you'll probably see, because the AP loves relating questions to real life lab experience. One of the things that you're going to see if you try to use pendulums in a lab is that while the equation says that the drop height shouldn't affect the period, it turns out that it actually does affect the period. So you will notice that there's going to be a difference between what you expected the period to be and what the period actually ended up being. So when you see a question like that and they say, hey, the person calculated that the period should have been 5 seconds, but when they did the experiment, it turned out that the period was actually 5.3 seconds. Why was that? Why was the period a little bit higher than what they measured? And what you would do is you would read the question and you would see whether they mentioned where the object was being dropped. And if they mentioned the object was dropped at a height usually greater than 20 degrees, then that's supposed to be an indication that the small angle approximation is, I guess you could say it's broken, no longer applicable, and that the period, the equation that we have for the period, the more standard one, isn't good enough. It's going to be a lot less than what we expect it to be. And the bigger that angle, the more these two numbers are going to deviate. That's pretty much the only reason why you would need to know this for pendulums. Like I said, it's nothing else than for a reason as to why the equation that we are going to use might not give the exact same period that we expect in class. All right, that's pretty much it with period. After this, we're going to talk about some motion graphs. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.